So right now we're going to be focusing on how trigonometry relates to forces, and more specifically, how we can use it to determine the magnitude of component forces when we're constructing free body diagrams or force diagrams and trying to quantify the effect horizontally and vertically an off-axis force has. Now we're going to start off with a quick overview about what trigonometry is and then try to explain how it returns to physics. So, the concept of trigonometry is first introduced in geometry, but really a lot of the more calculations involved with trigonometry comes in an Algebra 2 class. That is typically when we would be seeing the unit circle for the first time, and then trying to figure out how to fill it in. Now, when the unit circle is first introduced, usually a lot of theory goes into this, but the main thing that students tend to take away is what the values are going to be because, well, it is an overwhelming concept initially, and there's going to be a lot of values that you're expected to memorize. So I'm going to quickly go over what that theoretical concept was for how the unit circle was constructed, and then we can relate that back to physics. Now, right now, if you remember the unit circle, you might be able to fill in a lot of these blank spots, where right here, we would have 0 degrees with 0 pi for our radians, and the coordinate would be 1, 0. Then in quadrant 1, this would be 30 degrees, pi over 6, rad 3 over 2, 1 half. 45 degrees, pi over 4, rad 2 over 2, rad 2 over 2. 60 degrees, 2 pi over 6, or pi over 3, 1 half, rad 3 over 2. And then finally, 90 degrees, or pi over 2, coordinates 0, 1. And then you would just continue with having the same arrangement of the coordinates in quadrants 2, 3, and 4, just changing what the positive or negative signs were, as well as what the degrees and radians would be. Now, there was actually a way that we were able to mathematically determine all of those values. However, once again, I expect that our big takeaway from the unit circle would have been what those values were, because those are really what would have been tested on. But really, those values come from an understanding of geometry, which is why trigonometry is usually first combined with a geometry class. Geometry is the study of shapes. For a lot of history, the idea of pure shapes has been researched, investigated, and wondered about. Now, in historical times, the circle, specifically the philosophically pure circle, was a mathematical construct that philosophers pondered about. Because back when math was done either entirely in their brains, in oratory discussions, or trying to put it to tablet, a circle was really hard for them to actually construct and make it mathematically pure. So they tried to come up with approximations. The way that the first circle was created by mathematicians was they just took a bunch of sticks, and then they just kept breaking them in half, and then increasing the angle until they approached some object that looked like there were no individual lines, even though there actually were. But once they had that, they were able to look at a mathematically pure construct. And they were trying to look at the properties of each of these objects. In a circle, they were looking at the diameter, or the width of the circle, and then trying to relate it to the length of its sides, in this case the circumference. They found that a ratio of the diameter to the circumference would yield a ratio of 1 to 3.14. Or another way to put that, the ratio of the circumference to the diameter is 3.14. When they increased the size of the circle, they found that that ratio remained constant. It didn't matter how large or how small that circle got, as long as they were looking at a pure circle. We maintained that same ratio. They were able to extend this concept into other shapes in the application of geometry. One shape that they would have been looking at would have been the triangle. And they were trying to see if there were other ratios for the triangles like there were with the circle. That's also where the concept of pi came from. Pi, with that symbol that is the Greek letter pi, is the ratio of the circumference of a circle to its diameter, which was true for every perfect circle. Mathematicians were looking at those ratios that were true for every perfect triangle as well. So if we're taking this right triangle here, we could measure the lengths of the sides. In this case, 1 inch, 1.73 inches, and 2 inches. If we look at the ratio between these sides, we need to communicate what those sides are. So we're going to be starting off by defining an angle of interest. This angle right here, we will call 60 degrees. The side adjacent to it, that is the short side of the triangle, will be A for adjacent. The side opposite that triangle is O for opposite. And the longest side of a right triangle is going to be the H, or the hypotenuse. Now, when mathematicians looked at that relationship between these sides, one thing that they noticed was that the ratio in a 60, 30, 90 triangle between the side that is adjacent to the 60-degree angle and the hypotenuse, they found a ratio of 0.5. That was true when they scaled it up, and that was true when they scaled it down. 0.5 was the ratio of the length of the side adjacent to the angle of interest in a right triangle to the length of its hypotenuse. It was true for every right triangle where that angle of interest was 60 degrees. Now that is a very wordy way of talking about that relationship. That's why they did a mathematical shorthand called cosine. They said that the cosine function calculated the ratio of the length of the side adjacent to the angle of interest in a right triangle to the length of the hypotenuse. So every time they did a cosine of 60 degrees, they said that that value would be equal to 0.5. Likewise, if we were investigating other sides and other ratios in that same triangle, we would see different ratios. For example, the opposite side to that angle of interest to the hypotenuse was 0.866 in the small triangle, in the medium-sized triangle, and in the large triangle. That 0.866 was the ratio of the length of the side opposite to the angle of interest in a right triangle to the length of its hypotenuse. It was true for every single right triangle where the angle of interest was 60 degrees. The mathematical operation they used for that relationship was sine of 60 degrees. Now, this is not only going to work with 60 degrees, we can choose any angle. And when we plug it into a sine or a cosine operation, the numerical value that goes out, somewhere between 0 and 1, would tell us the ratio between the length of the side and the hypotenuse in a triangle. Now, the other trigonometric functions, such as tangent, secant, and cosecant, all talk about the relationships between other lengths of the sides in different arrangements. But really, whenever we're using one of those operations, sine, cosine, tangent, secant, cosecant, or cotangent, it is really just plugging in an angle in degrees, or radians, if the calculator is set up in that mode, and then the value that comes out tells us the ratio between the lengths of the sides. Now, the way that this relates back to forces is sometimes we end up with a force that is not directly on an x-axis or a y-axis. But we want to be able to explain it in terms of its horizontal or vertical effect on the acceleration of an object. This is where we can break it up into how much horizontally the force has an effect and how much vertically that force has an effect. These are our component forces. Now notice, this looks like a right triangle. That means that we can use our trigonometric relationships to try to analyze this triangle. Our component forces, or component vectors, are horizontal and vertical components of a force vector. Because they are parts of the vector, they are smaller than the original force vector. The combined effect of the two components is the same as the original force, but the sum of the two components is not the same as the magnitude of the original force. To determine that, we could just use Pythagorean theorem if we knew the lengths of these sides. A squared plus b squared is equal to c squared. but the sum of those two sides of the triangle is not the same thing as the value of the hypotenuse. However, this right here is not a great way to draw a free body diagram, because it implies that one of the component forces is not actually applied to the system itself. That's why after you have identified the component forces, we redraw them, starting at the origin for the object. So that way it looks like the vertical component is applied directly to the object, as well as the horizontal component. Now, the component forces, Fx and Fy, can be thought of as sides of a triangle. So using that magnitude of the force and the angle the original force has with the coordinate plane, the magnitude of each component can be determined. So this is really a triangle that we'd be looking at, where the hypotenuse is the original force and the adjacent and opposite sides are the component forces. This is where we can use sine, cosine, or tangent to really focus on quantifying the ratio between those sides and then rearranging these to be able to come up with a mathematical equation to specifically quantify any of the lengths of the sides.